Yarden, we can't hear you.
Now you can? Yes.
Yes, thank you.
Before the first quiz of Izal, we will have a recitation with that we will try within 1.5 hours to close some possible gaps in the course. I will speak either with Sophie or with another student that can help me find the exact gaps, what are exactly the things that are not fully clear after you submitted the project, okay? Because I think that most of the things that are not so clear during the lectures and then in the recitation and then you are in the project, it's kind of a spiralic understanding. When you are doing the project, you really have to understand it better. And then you have to study it differently and to apply all the ideas, right? So maybe if someone after the project can help me understand better where exactly are the gaps, what kind of issues or subjects are not fully clear. And then I'll prepare with, it will be in the week of the June the 3rd, I'll prepare a special recitation to have a kind of closing the gaps towards the quiz with questions from previous exams of Izal. And I believe that when it will be like this, things will be more clear. And I'm really happy that you told me about it, and we'll try our best. But I know that all of you knew that this is a very heavy load course. It has always been like this, and it's not that we compressed the course into 10 weeks. We did reduce some materials, even if you don't really know all that is going backstage. But there are a few things that we want you to understand deeply, and this is the things that in the beginning of the course we speak about them, the more heavy mathematical ideas. And then some of them we took off, for example, optimization and PCI that I don't know if we'll have the time to speak. And if we will, we'll take off some other lectures by the end of the course. Okay? So this is about that. And about the project, I've been asked if it is possible to give another postpone, and unfortunately it's impossible. But if you wish to submit later, and some students did come to me specifically and talk to me about problems, personal problems that they had, so that they cannot submit on time. And in such case, we'll give you 2 or 3 more days without reductions of points. But if you don't ask, you take into account that you will be 10 points reducted. Okay? Good. But and anyhow, don't submit half project. We prefer that you will submit and have this 10 points reduction, and not that you submit 2 questions and not at least almost all of the 4 questions. Yes. Yes. We can speak, you and I can speak privately, because we will speak about it. I believe that it is better to speak about it privately, and then I can ask you and see some of your answers, and maybe I can tell you that you spend too much time about this, and just spend a little bit less. And I believe that everyone in the class can do it by Friday. And in very special cases, we will have a delayed submission. Okay? Yeah. It's from Izar. It's independent of my schedule. I know that the first quiz is should be at the 10th of June. For this reason, we ask you to submit the project 1 week before, so that you can have also at least first response and grades, because the projects are the main way to study towards the exam. Project 1 you have to submit by this Friday. Yes, you will have much before, I believe. I don't know, because we didn't have such a big course for few years, but years before it took a few days to send a response, and we will see what will happen this course. Okay, so let's speak about our recitation today is about TIH, hazard, survival, and so on. I thought about starting from the mathematics, but we will do it on Sunday. So what I want us to do now is to understand the more basic terms and let's say kind of sum up and show you practically how we understand these ideas, okay? Not with all these mathematical equations, but to solve some mathematical questions, sorry. Okay, so let's do it that I will ask a student to read, and then the student will try also to explain what he has just read. So the first definition is very easy. Who would like to read and explain? Yes. Great. So what does that mean? It's okay. You don't have to explain in your own words.
Oh, yeah, it just means how much time elapsed.
Great, and a great explanation. And when he read it, I felt like I'm going into Khan Academy, right? Because you have quite a radiophonic tone. Okay, next one, medium. Who would like to try the medium? It is written here, and you just need to try to explain it in your own words. And if you prefer to explain in Hebrew, I will translate. It's okay. Sophie? Hamas is this. Yes, the distribution of the ISIs. It's okay. Yeah, so please try to explain what is this. You have several ISIs, and depending on their size, Good. And I have a question. If you remember from last time, we were talking about the distribution of ISIs. Do you remember what kind of distribution was it? In a Poisson neuron? Exponential. So let's look at this distribution. So it should look something like this, right? So that the TIH of a Poisson neuron is an exponential distribution. Therefore, most of the interspike intervals are small and only very few are big, right? This is ISI size and this is the probability. And of course, is this a PDF or a CDF? Right, histogram is commonly, no, it's always a PDF. Okay. PDF. Okay, a bit harder. Who would like to try the survivor function? Da, da, da. Yes, Almin. Yes. Right. Great. And I wish to ask you, would you like to try to explain this sentence? Because I think this is not the fully clear one. Would someone like to explain the probability of observing at least one spike up to the specific time point? So that means at least one spike, there is something that misses here since the last spike, of course. It's not just any spike within any moment, but since the last spike. So just think about it as if you're hitchhiking spike. Okay, and then there was a spike and you missed it. And you want to know how long would you need to wait until the next spike. Okay, so this is what the survivor function means. So I've been waiting 10 milliseconds. Does that mean that probably I could have hitchhiked another one or not? Okay. Is that more clear now? Because I don't want you to go into the math. I want you to understand the definition. Within a few moments, we will combine it with the math, given a very nice and simplistic example. Okay? Any more questions? Yes. Thank you, Aylan. Please read the next one. Hazard. So this is just about the difference. Can you please explain it to everyone? If you feel like you can. Right. So let's go again at this idea of hitchhiking spikes, okay? So I just missed the spike or the bus or whatsoever, and I've been waiting for 20 milliseconds and no spike arrived. So what the probability now that I will see another spike? So do you understand the difference? In this one, for example, I've been waiting 20 milliseconds, and when it was 10 milliseconds, already a spike was occurring. Okay, so here I don't care if a spike was occurring or not. I'm just asking myself, I've been waiting 20 milliseconds. What is the probability that I saw a spike? It doesn't matter when. At this one, it says I didn't see a spike so far. Therefore, what is the probability that now it will come? Okay. Again, it's a bit, we will do it in a second with a very nice example. Okay, and the last one that we will go back. We'll go back to it after we understand the hazards. Yes, Julio? Good.
Correlation between the signal at the two different time points in a time series.
Yeah. Okay, so I want you explain it really nice, but I want to be more clear. what would you say that the main difference is between the autocorrelation and all the other functions that we were talking about? Okay, I can agree.
Being related instead of being related to a single point in time, it relates.
Okay, this is about the x-axis. We will talk about it more, but the main thing about autocorrelation is that it is not a measure of the ISIs. In autocorrelation, we don't care whether this spike were adjacent, right? Because in this TIH, I ask myself between the last spike and the one after. Okay, so this is the ISI. In autocorrelation, it could be between any possible pair of spikes. And this is the main difference. Okay, and we will go back to it after we understand more thoroughly the hazard and the survivor. Okay, so I'll close now the screen and we will do a nice yes. Yes, it is right. No, sorry. Good. Okay, so let's have two nice examples of how to calculate this until the hazard. We won't do the autocorrelation now. We will do it in a minute with something different. So let's say we have a neuron that can that has three possible ISIs, only three possible, and they are randomly chosen from uniform distribution of 5, 10, and 15 milliseconds. Okay, that means that when there was a spike, the next one could be either within 5 milliseconds, 10 milliseconds, or 15 milliseconds at equal probabilities. Let's start with what is the histogram of the ISI, the TIH. How does it look like? Yes, Julio. Good, because it is equal probable for each one of them. So it's this one, and this one. And you can write here either the probability and it will be third, or the percentage and it will be 33%. Yes. Yes. Good. Now we want to calculate the survivor. And in order to calculate the survivor, we need to calculate first the CDF, right? This is a PDF. So let's go into the CDF. How would you calculate the CDF of such a function? Good. So where are the steps? So it begins, the steps in the x-axis is 5, 10, and 15, right? And then you begin from 0. And there is a jump here. This is third to 10, and another jump here to 15, and from 15, there is another jump to 1, right? Oh, sorry. Is that clear? Good. Now the survivor function, let's think about it as a kind of a game. that you stand here on the podium, and if a spike occurred, you fall through a hole, okay? So let's ask ourselves, what is the probability of me to survive the spikes, okay? Therefore, the CDF represents the probability that there was a spike by this time. For example, the probability that there was a spike by 7 is a third, right? The probability that there was a spike by 12 is 2/3. But the probability of me surviving and not falling into the hole due to a spike is the 1 minus the CDF. Yes.
Did occur. Now you're saying that there wasn't.
Yeah, sorry. So the survivor is that the spike, at least one spike up to, yeah, you're right. There is a mistake in the recitation note. It's the opposite. It's the probability of not observing at least one spike up to a specific time point. Okay? Thank you, Austin. And no spike. The probability of not observing any spike up to a specific time point. Yes. Oh, thank you, Sophie. This was exactly what I wanted to ask you how to draw. Yes. So the survivor will begin. This is survivor. And it will begin with 1, and then you will have by 5, 10, and 15. So it goes like this. Here it's 2/3, and then like this, and another third, and like this, and then it's 0. Okay? Good. And now the hazard. So let's look at it again. If I'm on the 7 millisecond, what is the probability that I survived? Here by 7, it will be 2/3, right? Because there is some chance that there was a spike in the 5. It's only 1 out of 3 possible trials. But where I am standing, there couldn't be another spike, right? So now we can ask ourselves the hazard question. If a spike didn't occur by this time, what is the probability that it occurs now? Okay? So let's take again the x-axis of 5, 10, and 15, right? So what is the probability that if I've been waiting 3 milliseconds, okay, that there will be there was no spike so far? What is the probability that there will be one now? At 3 milliseconds, 0. Very good. I'll use here the black. And this is true for all numbers until 5. What happens at 5? If I've been waiting 5 milliseconds and no spike occurred, what is the probability that the spike will occur now? 1/3. Right. Oh, sorry. It's the black. So it's 1/3. It's over here. Right? And if I'm on 6 milliseconds and no spike occurred, what do you say? Is it 1/3 or something different? Why? Who said? Yes. Yes, Neil. Yes, it's you. Sorry, I'm a bit. It was Sophie. You're right, Sophie. Please tell us why. Okay, so again, please leave the formula out and just answer my question. if I've been waiting 6 milliseconds and the spike didn't come, the bus didn't come, would he come now at 6 milliseconds? No. So when would he come? 10. So until 10, it looks like this, right? So I had this jump, delta function here and another zeros here. I reach to 10. What is the probability now? Okay, it didn't occur at 5. Therefore, there are only 2 possibilities. That it will occur either in 10 or in 15. And this is a uniform distribution. Therefore, great. Is that clear? Yes, exactly. And then I waited after 10, it didn't come. So now it has to come at 15. Is that clear? This will be 1. 1, because if you waited for 15 milliseconds and it didn't happen at 5 and by 10, it has to happen at 15. This is not a PDF. This does not sum up to 1. This is a Bayesian probability. And as Sophie said before, this is a division between 2 probabilities. Therefore, it might be bigger than 1, as you see here. Third, half, and 1. It's bigger. Yes. 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 I was just about to ask if someone read that book. Sophie, tell us the monkey hole problem. It's just about that. You're right.
The presentator, the animator of the TV show, will ask you to choose the door, and then we show always the door which should go behind, and then we'll ask you to change or not the choice. And I will take this or not.
The question is it yes.
And
Yes, yes.
select the first door here inside. We have now one. No, okay, before to open it, we have 1 chance out of 3 to have a car. But as soon as the first door is opened, you now have 1 out of 2. If you change your choice, so you have more chance to find the car for the choice. And fun facts about that. I think it was a woman that found this.
Really?
Yeah, and the mathematical community was like, no way, haha, that's it, but because she was not in the mathematical field, but actually she was so true. And second thing also that human tends to stay on their choice, while when we do that with pigeons, they finally change the figure.
Yes. If they change the that was really cool. And another fun fact is that there is a book that they explain this solution that is called the strange. Yeah. Yes, and it is like kind of a book that was written by an autistic savant who is a mathematical savant. It's really, really cute. I think it's American. So we highly recommend this book. Yes, great. So you can read also the explanation over there. And thank you very much, Sophie. Yeah, you know that I thought about writing about it, and then I say, students won't like it, and this is. But I'm so happy that you know it. So now what I wanted to show you is a solution that I wrote, a computational solution. And now I see that there is a mistake within this solution, because instead of using the steps and so on, I just plotted, right? Instead of doing like this, that we did here, it here very accurately. In my solution, I just plotted I computed the dots right, but I plotted it wrong. So maybe it will help some of you just to kind of how to start with your project. And you can see that the idea here, how I do it, is that I really keep on writing very clear names for my variables. So I have the opening variable, which is the ISI, right? And I calculated the PDF over here. And then when I want to plot the TIH, I just need to know the syntax, but I know what I'm looking for, right? And so you can see here, I just plotted 3 bins with the level of, it should have been 3rd, and I'm not fully sure why is it bigger than 0.6. Okay, so there are some mistakes here. But here I want to show you, for example, the hazard function. So you see that the basic idea is that I write a survivor vec for hazard, right? And then I know that the survivor was, I computed before. So this is 1, 2/3, and then 3rd. And then I divide between the PDF and the survivor vector. So I take completely the formulation. And then this is just about the relation between the mathematical aspect and the computation, that you can do it only when you write the code. Because when we did it here, we just used our logic in a way, right? But then when you compute it, you can really understand the relationship between them, and not only understanding the question. Okay, so this was just about the hazard. I will see if we have anything more. So just some important notes. So please note that the hazard is Bayesian probability. So if it does not sum up to 1, this is not a mistake, right? This is non-negative if you got negative values, so there is a mistake. And we said that it's not a probability function, therefore it might even go to infinity, and this is okay. And here, maybe you remember from his lecture that the hazard of a Poisson distribution is constant. And this is representing that the process is renewal, right? Because it has nothing to do, if I say that I don't care about the question whether a spike occurred by now or not, the probability is the same. Therefore, the hazard function should be a flat line with the probability of the rate, right? This is what is written here. Do you understand why? Let's try to look at it. So if it is a straight line, that means that at 3 milliseconds and then at 7 milliseconds, you ask yourself, if a spike did not occur by now, what is the probability that it will happen now? It's 50%, okay? And if it didn't happen till now, it's still 50%, because it's independent on what was before, okay? So, and now I want to show you this idea with another kind of discrete Poisson distribution. And please note that as long as the ISI are longer, then the hazard function becomes more noisy. And this is only due to the fact that we have a final sampling. Okay? Okay, so let's understand more deeply the idea behind the discrete Poisson distribution. So we have a neuron with a firing probability of pt, which means that only at the time points from the given series t equals nt, it has the probability to fire. Okay? Let's try to understand it. What does that mean? This means the following. So now I want to start by writing all the possible ISIs that I can have. So let's say, for example, that t equals, we'll go on with the 5 milliseconds, okay? 1 minute. Therefore, all the possible ISIs are only multiplications, full multiplications of 5. For example, 5, 10, 15, 20, 25, and it goes to infinity, right? Okay. And this is the probability of, so therefore the P is just kind of taking all these possible ISI and 1 minute. Yeah, okay. It's taking all these possible ISIs and they have the same probability. Good, okay? Yes, Rachel.
So in that case, where we saw that the hazard function was going upwards, then that's not a possibility.
This is not, no. Okay, so let's see how it looks like. Okay. So, sorry. The question is, and by the way, this was given from one of Izar exams, okay? So he says, plot the survivor function and the hazard. So how would you start to solve it? So you say the following. I know that to compute the survivor, I need to compute the PDF and the CDF, right? And then I can do 1 minus the CDF, which will be the survivor. And the PDF over the survivor is the hazard. Is that clear about the strategy, how to solve it? Okay. So let's look. So to calculate the hazard function, we need to calculate the probabilities for given ISI. Okay, so let's say we have the bin sizes with a width of t. T again, for example, could be every 5 milliseconds. No, it stays like this. It stays kind of theoretical for any given t. So you write on your t-axis, your x-axis, you write t, 3t, and so on. Okay? So the probability for an ISI to be, for example, 15, how do I calculate it? So I say, if the ISI is 15, that means that there was no spike before, right? So I can say it's the probability of 1 minus the probability of a spike powered by n minus 1, right? Do you understand why n minus 1 here? And this is multiplied by the probability that the spike will occur now. Is that clear? N minus 1 because it didn't occur by 5 and 10. And these are the, if I ask about 15, I will look 2 samples before. If I ask about 20, I will look at 3 samples before. Each time I will look at the previous samples. Good. So now we need to calculate the CDF. And the CDF, we know that this is a cumulative function, therefore this is a sum. Okay, so maybe you don't know this way of writing a sum, but this means that you're writing for each multiplication, for example, for 15, n equals 3, right? So I'll use here 3, and then I will calculate the probabilities so far for 5, 10, and 15. And this will be the CDF of 15. Do you understand it here, what it says? Is that new for someone? Please feel free to ask if you didn't understand so far. Okay, so now what does that mean? Now I need to sum up all the possible probabilities. So this is P times 1 minus P, 1 minus 1. I take this function over here, and then I just write it again and again. So the index that I should replace each time is n, right? So in the first one, it's 1. In the second one, it's 2. In the third one, it's 3. Okay? And when I do it like this, I can say that this one equals to 1, right? And then I write all the other powers over here. I just started to open the sum. This is an infinite sum, of course, but this is about the AP. It could, I mean, like it could come to infinity. So now, how can I compute it? So we know that P is smaller than 1. Therefore, we can use the geometric convergence. Maybe you remember it from series in high school. So what does that mean? This is a geometric conversion that you have the same A, which is a variable that stays the same for everything. And you have here only the powers that change within each one. And of course, in such an exam, we write you what is the geometric convergence, and you can write it also like this. And its convergence, it's the constant multiplied by 1 minus r powered by n divided by 1 minus r. Okay? Therefore, we take all that we have written so far, and I wrote it by colors that you can follow. So you can see that the A is the P over here, and 1 minus P is the R, and K is the same K here, and then this is equals to P, 1 minus R powered by N, and 1 minus R, okay? So now we have a constant, which is the CDF for each possible time interval. Okay, and this is a bit heavy math, but we can start putting here the possible n's, and then we can start to plot it, okay? Yes?
Based on what we have described earlier, would it not be n plus 1?
Why n plus 1, sorry?
Because we stop at the sum of n minus 1. But we're wanting to take all the way up to the current.
Ah, okay. Yes, yes. Yes, it doesn't matter because it's at this specific point there is the change. Okay? Okay, yes. Of 15, yes. So the CDF of 15, let's say that our probability is 0.3. Do you need also the probability? Good. So for the CDF of 15 equals to the probability of 5 plus the probability of 10 plus the probability of 15, right? And the probability of 5 is 0.3. The probability of 10 is, there was no spike at 5, therefore there is 1 at 10, so it is 0.7 times 0.3. And the probability of 15 is 0.7 square multiplied by 0.3, right? And this is the direct calculation. Now let's see if our formula that we did over here gives us the same. So the formula after you delete everything is 1 minus 1 minus p over n. So this should be 1 minus 0.3 over 3, which is 1 minus 0.7 over 3, which is kind of saying there were no spike by 15, right? And this is the completion. So this is just, yes, so they should be the same. Let's see if we can see it over here. I believe that it has to be, right? Yes, great. So now let's look at the survivor function, and then you will have a short break. So the survivor function is 1 minus the CDF, 1 minus 1 minus 1 minus p powered by n, and then you have 1 minus p powered by n. So the other function is the probability of the ISI to be equal, which is 1 minus p n minus 1 multiplied by t, and this is divided by the survivor, and this equals to p, right? As we expected, because this is a Poisson distribution, the probability is independent on previous events. So you can see, for example, a nice drawing over here when it equals to 0.3. So these are the 5 probabilities that were given here. Therefore, these are the possible ISIs, right? And the CDF is a step function that within each function, you see the ISI becomes smaller because there is a lower probability the longer you are. So therefore, in the CDF, the size of the step should become also smaller. And then in the survivor, the steps are opposite. And in the hazard, it is a flat line. Okay? Was that a bit more clear? You need to think about it and maybe to practice it yourself in your second project. But now you know what you need to expect, beside the fact that you have a refractory period. But you will also have the without refractory period, and then you will see that your codes are working because they need to give you these results. Okay, 5 minutes break. And then we will talk about autocorrelation and cross-correlation, which are the same, but different. Yes.
Add the noise to question 2D as a 50 Hz sine wave. But I was a bit confused because for me, if it's noise, then it should look noisy. And
You just don't see the signal because there is too much noise. Yes.
okay.
Yes. This was what we expected to happen.
So, because if instead of doing just dots, I just connected with lines, it really doesn't look like noise. It
Really?
just looks like
Yeah, because you see only the noise, right? You don't see the signal itself.
so it's
Maybe.
okay.
I think yes. Yes. No, I show you how. You know what? I will say it in a minute in the class. The reason I show you how to write it because when you have, for example, in exam or quiz with exam, that you have this kind of a question. So I want to show you how to even start, right? And And now we will do another thing about autocorrelation that I hope it will be also more clear.
Any notes to remember the formula?
Commonly, when we need something like this, for example, geometric convergence, we give you the formula because I don't remember it by heart.
No, like not only the convergence, but the other.
Sometimes it's even too much formulas. For example, I don't know if you remember, there was this Gaussian and it gave you, for some reason, the באתר. I have a question. There are some questions that I want to show you from past exams, and I'm not sure if we'll make it at today's recitation. Would you like us to continue at the reinforcement or next recitation? Or staying today for another 15 minutes? So can we finish today by 3:45? Is that okay? And then I will run to my child.
ירדן?
I don't. There was the meeting at 1, right? I didn't hear you well, so please repeat. Yes. Yeah, I wanted to do like a very long one and also go into the details with the Izar formulas. But I'll speak to Sophie or to one of the students because I'm not fully sure whether there is a need to go through the math of autocorrelation and cross-correlation, because I think the recitation is enough, but I wish to ask you, how do you feel about it? No. I think that you know what? I don't know. You need to ask Izar, but commonly it gives all the formulas which are not from the course. So it should be fine. הייתה שאלה, נועה?
כן, רק פשוט אם את יכולה לעשות שיתוף מסך
אוי. תודה על
תודה.
ההערה. למרות שנועה, דווקא עכשיו אני פותרת את זה על הלוח.
סבבה.
Okay. So, Armin, please remind me, what did you ask about the formulas, if you need to memorize? That was the question. I don't know, but it's commonly analytical, like the one that we did here. Yes, on paper, and this is considered a very, not a very, but a tough question. Yeah, a tough question to answer. Yes. Because you really have to use like a kind of all the formulas, and you need to understand how to calculate the probability of the ISI. So it's easy to understand it, but I'm not fully sure how straightforward it is, right? So this is a bit more high level. In the quiz today, you will see something that I think will be more similar to the level, to most of the questions in the level that will be in the quiz. And this is one of his favorite subjects, so very high chance there will be questions. The what? The quiz, probably 1.5 hours. I don't know yet. Yes.
So reaching a meaningful solution there requires remembering.
No. You don't need to remember any formula. Probably you will be given with any formula that you need.
You don't need to start brushing up on it.
No, of course not. No. No need. Yeah, if it helps you, if you feel that it will help you to understand, maybe try to do it t equals 3 at a probability of 0.6 or something like that. No. This is considered a high level question. I don't think that this is the kind of a question that you will have. And I can send you more questions, but I think that now you should just kind of have a taste, focus on the second project after you finish the first. And after you compute it, I think that you understand it much better. Yes. Excuse me, there? No. This is only my questions in the project. And I wanted to tell you, I forgot that regarding all the autocorrelation and the cross correlation, there is a very, very cool app that Benji wrote the code, and that you can kind of add in neurons and the relation between them. For example, this one excites this one and this one inhibits, and there is the delay and how much, for how long it inhibits and so on. Maybe we will play with it, and then it just draws the autocorrelation and the cross correlation functions. Really cute. Okay, so I don't know if we'll make it today that we will cover all of the autocorrelation and cross correlation. So probably on Sunday, I think that we'll just go on with the examples here, and maybe I'll give you more. I think this is this week at Sunday we did take Izar presentation, and I showed you how to understand and how to come toward classes that you understand better the things. Now this Sunday I can either do the same with the upcoming presentations, or we can go on with more examples like this, or we can save some of the examples to the end of the quiz preparation, but then we won't have enough time. So I don't know, Sophie, can you open a poll just to let me know what do you prefer? I think that the right thing is to finish this. And I think that now you're kind of starting to understand that the recitation kind of covers most of the aspects from the lecture. So the lecture is might be a bit more vague, but the recitations are very, very practical. So now I want to show you. I want to start by a nice exercise that we are going to play. And I hope that by this exercise you will understand why there is a need for autocorrelation function after we did all this hazard. So let's say that we have a neuron that he has two possible inputs. And when this one gives an input, the neuron fires a spike within every 3 millisecond regular spike. And this one fires within 5 millisecond regular spike. Okay? So this is kind of a mixed regularity in this neuron. And now let's see if there is an input only from the 3 millisecond regular spike. So we can write here an index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I hope that you will be able to see through. You will. Here, 13, 14, and 14. This is a full period, right? Because here at 15, it will be just exactly the period that the two spikes are firing together. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And let's have this 15 so we can count a few more things. Okay? Now, when there's this input, this neuron begins with a spike here, and then here, 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 and here, right? Every 3 milliseconds, therefore, it should be an exact multiplication of the number of 3. And when there is an input coming from here, it will start here, and by 5, 10, and 15, right? But on 14, it won't have 5 milliseconds. This one? But then you don't have 3 milliseconds in between. There is a chance that I did a mistake. This morning when I explained it, I did a very big mistake. So I didn't sleep this night. So if you find any mistakes, there is a very high level that you're right. Do you think that something is wrong here? I'm not sure myself. Okay, but let's go. I think that it's okay. Right, so 0, no, no, yes, no, no, yes, no, no, yes, no, no, yes, no, no, yes. I think. Okay, so now let's say that this neuron got the two inputs together. So how would look the spike train of such neuron? So here at 0, there will be 1. By 3, there will be 1. Here at 5, also another 1. At 9, also another 1, 11, and also by 10, and 6, oh my God, and 12, and 15. Do you see the marker? Okay. So please tell me, what are all the possible ISIs in such a spike train? Just count all the pairs of neurons which are adjacent. This is what you need to do to answer my question. So one possible ISI is these two, which are 1 millisecond, 1 minute, and we will count them, okay? Don't worry. Another possibility is 2 milliseconds and 3. Could there be 1 for 4? 4? What do you think? Yes or no? Let's think together. ISI, only interspike intervals. So given the fact that this one fires within every 3 milliseconds, there is no way that there won't be 3 spikes, right? 3 beams with no spikes. So 4 milliseconds is irrelevant for the ISI. Now I'm back into the ISI analysis of we use for survival and hazard and so on. I just want to show you why we need the autocorrelation. Yes. This is not an ISI, right? Only between adjacent spike trains. Maybe the fact that I used black and black here is a bit misleading. So let's have the red. This is the autocorrelation. Now I speak only about the ISI. You are right, within 1 minute, we'll go into the autocorrelation. But now I want to speak only about first order ISIs. Yes. Yes, yes.
Why, like, I'm only seeing max two bins of no spikes. So why is it?
No, you were just explained. There is maximum 2 beams which are blank, right? This is the maximum. Therefore, we have 3 milliseconds and we don't have 4. Because for example here, due to this input, this neuron had 3, and this neuron did not have the time to have the 5, right? So this is the 3 milliseconds. You mean, okay, 3 milliseconds, it means 2 blanks. 1 millisecond means that there is no blank bin between them. Good question. Okay, so how many do we have like this? Let's count. Okay, how many? How many do we have of 1 millisecond? We have this and this. Why? We are looking at all the times that we have 5 and 6, or we have multiplications of 5 that are either followed by a spike or they are prioring a spike, right? And this happens only at 2 possible numbers, 5 and 6 and 9 and 10, right? Okay, 2 milliseconds, how many do we have like this? 1 and 2, right? So we have 2. And why is that? So we can look again at the 5 millisecond regular spike, right? It will be easier because then we ask ourselves, this one fires at 0, 5, and 10. So now we need to look at this one and look if we have a neighbor either at 3 or at 7. So this will have, so 5 will always have a 3, and 10 will always have a 12. Okay? And now for 3 milliseconds, how many do we have? 3 milliseconds. So we have from 0 to 3, and from 5 to 6 to 9, and from 12 to 15. So we have this count, which means that the probability for each one is 2 over 7, 2 over 7, and 3 over 7. And by the way, today I also did it without writing the 15, and then you don't have this one, so you have third, and third, right? But then when we look at it, it looks like this is not a regular neuron, right? Because when you look at the TAH, and you have here the ISI and its probability. So you have 2,7 and 2,7, it's here, and this is 3,7. And this looks like it is not a regular neuron. Because if I would have asked you before we were plotting this, you would have probably told me, oh, this is simple. You have a TIH that looks like this, either by 3 or by 5, right? But now you have at 1 and 2 and 3 because of this mixing effect. And for this reason, we now understand that only looking at the ISIs of the adjacent spikes does not provide us enough information. Because let's say that we have here another neuron. And this neuron fires, okay, he waits for a spike. And then if another spike occurred within 3 milliseconds, then it will fire. Okay? And now we want to ask ourselves, when does this neuron fires? What do you say? So he has a spike, and I say, okay, now I need to listen if there is another one within 3 milliseconds. And he doesn't care if there was one at 1 or 2 or 4, he doesn't care. He asks himself only if there is one in 3. So when would that be? Yes, Giulio? Okay, so of course he will have, I want to use another one. So here he will have it, here, here, and here. This is the easy one, right? Would he have another? Because he heard in 0 and then he needed to wait 3 milliseconds. Excuse me? Yes, it's after the second he fires. Okay? But I say that he fires after he got the second one. Now he needs to prepare. He has the cue, listen. And when he hears the one within 3 milliseconds, he fires. So he fires after the second one. Okay? Yeah, so of course, at each one of these spikes, there are 3 milliseconds from each other, irrelevant if there was this spike or not, right? And another thing is that this, do we have another one like this? 5 to 8, 5 to 2, 10 to 7, 10 to 13, no. These are the only possibilities, okay? Yes.
So it is exactly.
Yes. Yes. But this neuron does not care. Let's see, for example, he heard this spike over here. It was his cue to listen. And then, sorry, he heard the spike over here, right? This one. And then he did not care whether there is a spike over here or not. He was waiting for this one to fire. Now, this is might be a bit strange mechanism, but it is kind of the basic idea behind SynFire chain, which is a very interesting theoretical idea that also has some findings to support it, that neurons don't care about the noise. They care about specific timings of firing spikes. And their calculation is synchronized on the durations and not on the question whether there was a spike or not. And for this reason, we have the autocorrelation, because autocorrelation does not look only at adjacent spike, but also at spike that has this interval. Okay? So I showed you this because for example, if you have a question in an exam, and maybe we'll see. Oh, I want to show a few things about autocorrelation, and then was that clear? Maybe not fully. Okay. Okay. I just wanted to show you that only adjacent spike not always carry the full information. Okay. And I wanted to show you how do I start by counting the ISI, and when I try to compute the autocorrelation, I do the same but for all possible distances. Okay. So for example, in autocorrelation, we will also have 4 milliseconds. Do we have something like this? So I look if I see from here to here, from 0 to 4, from 1 to 5, from 2 to 6, from 3 to 7, right? And I think there is, we have from 6 to 10. So we have 1 like this, okay? And then I go on with the 5 milliseconds. How many do we have like this? That they have 5 milliseconds? Sorry, 1 minute. How many do we have from 0 to 5, 5 to 10, and 10 to 15, right? So we have 4. And I start to count them, and then I can start by calculating the autocorrelation, okay? Yes, Austin.
5.
Ah, yeah, sorry. Okay, and also when you compute the autocorrelation, this is what you do. You say, okay, let's see if there is a spike in 0 and in 3, in 1 and in 4, in 2 and in 5, in 3 and in 7. Okay? And then you count them, and then you start normalizing them. This is the idea. Okay, so I'll show you another nice visualization of this. So this is the quantity for autocorrelation, that you take the same signal and you shift it, right? And then whenever you see a count, that means that you should write here 1. So for example, instead of doing look at 0, look at, if I want to see the time lag of 0 and 3, 1 and 4, 2 and 5, I can do it either like this, jump in, or I can take this and I can write it again, shifted by 3. Okay, I want to show another way. So I go back to this example. Please tell me what is not fully clear, because I really want you to understand. And I think this is a nice story problem. What is not fully clear so far? Was that okay? Okay, so if I want to calculate the autocorrelation, so I can do 2 things. I can start writing to myself all the possible time lags. Why do we call them time lags? Because now it's not about only ISI, it's all the possible orders, the ISIs, which is kind of a phrase that I don't really like, but let's use it. Okay. And then we know that for 1 within this period, we have only 2 like this. And in 2, we said that we have 2. And in 3, how many do we have? We have only 3. Yeah, I think that you're right. And in 4, we said that we have 2. And in 5, we said that we have 4. Okay, and then I go on like this, and this is the count. And then when I calculate the probability, it is written here. Excuse me? Sorry. Where? I was just looking for it. From? Where again? Sorry. 3 to 6. Oh, I wrote, oh, sorry. Of course, there are 5. And for 5, it's 4. Yes. And then I start normalizing it. After I counted, I start dividing it by the number of spikes, right, that I have. So what is the number of spikes that I have by 15? 1, 2, 3, 4, 5, 6, 7, 8. So the probability here is 2 over 8, 2 over 8, 5 over 8, 2 over 8, and 4 over 8. And the reason we don't like probability is that it is highly dependent on the length of x, right? Because here I counted only until 15. So now we regular it by the bin size, right? So the bin size is 1 millisecond, and then we can have the rate, okay? And this is about normalizing. Now I want to show you, yeah. Delta T is the bin size. Wait a minute. This one, sorry, I said something wrong, and this is why you are confused. Here, this depends on the length of my recording, right? I was recording here only 15 milliseconds, therefore this is my count. Now, so therefore we want to divide by the number of spikes. So it won't be dependent on the length, one milli, sorry. But then we can say that if we have a bin size of 1 millisecond, or we have a bin size of 2 milliseconds, okay, so this will be 1, 1, again here, 1, here it also will be 1. The bin size that you take 2 milliseconds here. Excuse me? Yeah, so here the delta T, it will be 2 milliseconds here, right? Yeah, here the bin size is 1 millisecond. If I would have the same recording, but with a lower resolution, that I would record every 2 milliseconds, then my spike trend would look like this, right? It will be 1, 1, 1, 1. It will be different. And then if I count it, it will be different than this one. Therefore, we can divide by delta T, and this is called the rate function of the autocorrelation. Ah, no, I meant delta T is the bin size. It should have been, I don't know. Sorry. No, it's my bad, sorry. Delta T here, it's 1 millisecond. So if you want to write it as rate, in rates, we write it as spikes per second. So we need to divide by 2 over 8 is 1/4, and 1/4 over 1 millisecond, which is 1 over 1,000, right? And this will be 250 hertz. And what does that mean, the rate? This is kind of the way of saying what rates do we have in our sample. And this gives us the kind of the list of all possible rates in our sample. Yes, Neil, sorry. We can do also 6 and 7. Yeah. By the way, 6 will have to, of course, be from 0 to 6. We will also have quite a lot, right? But do we have at 7? Let's spin. 0 to 7, 1 to 8, 2 to 9, 3 to 10 we have. Okay, so one way is counting, like saying 0 to 7, 1 to 8. Another possibility, which is the computational way, how when you write autocorrelation, the built-in function, it does something different, okay? Instead of looking and saying 0, 3, 1, 4, it copies this spike train and shift it by the number of bins, right? So for example, if I want to count how many do I have in, pick a number, Sophie? 4. So I will take these bins. Okay. Where? Oh, good. Yeah, I said that I didn't sleep. So if you want to look at 4, what we will do now is just take this and shift it left, right? And then when we shift it left, this one will be, let's add it. This one will be, okay. So this one, instead of being here, it will be here. And this one will be here, and then here, 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 and the last one is here, okay? And now instead of saying 1 to 4, 2 to 5, and this might take like a very long time, when you shifted it, what you see now is how many spikes are the same at the same column. And then you see that there is one here and another one here. And this is the spike count. Cool, huh? Okay, so few things about autocorrelation. So first of all, for discrete signal, we use the definition, which was written here. And I showed you 2 ways to count. One is just by a loop that counts within each index, okay, for each possible duration. And another one is just by shifting and then looking at how many spikes we have at the same column. We shift it by the number that we want to write. So for example, here, Sophie, she chose to shift by 4. Therefore, next to 4, we will write 2. Yes, Araceli. Okay. Now, please note a few things. First of all, in the autocorrelation, this will be the x-axis, and each one of these can be the y-axis. Okay, so this is a very common confusion of students, that they think that the autocorrelation is the interspike interval or time or whatsoever. No, this is called the time lags, the size of the shifting or the size of the possible orders of ISI or whatsoever. It is called the time lags. Okay, so this is what I told you about the constant reference and the moving target. Therefore, number of shifting bins. Now, some of you, and you might, I don't remember if you have it in this project or not, maybe we took it off, that sometimes we use the autocorrelation on, not on spike trains, but on EEG and so on. And then you just do the same, but you compute the Pearson correlation. So you shift the signal, and you compute the signal correlation after the shifting. And this is also called the autocorrelation function. When? Yeah, but here we did it for a spike train. But then, for example, please remind me your name next to Ella. Ofek and Ella, both of them are in a lab of EEG. And when they want to compute autocorrelation, how they do it, they take this continuous signal, and then they copy it, and they shift it by the size that they want, and they compute the Pearson correlation between the 2 overlapping signals, And this is the autocorrelation function of not a spike train. And it's really nice because it finds the periods, right? So I wrote here like the sanity checks for autocorrelation. So in autocorrelation, you have to define the max time lag because, as Neil said, we can go on until infinity, but we don't need. In neuroscience, it is commonly used as 100 and 200. Autocorrelation must be symmetric. If you shift it backwards and or forward, it should be the same. And we prefer to assign 0 at n equals 0, a time lag of 0, because otherwise it will be very, very high and we won't see the autocorrelation itself. And we're not interested in correlation between signal to itself. It is meaningless. All of this should be when you compute the autocorrelation, either if you used a built-in or if you ask ChatGPT, or I don't care, or if you write it yourself, which is, I think it's the best if you really want to understand it. But please know that you have to do each one of them, and we will reduce points if you don't do them, okay? Now, this is a very nice, by this I will finish because I see that it is impossible to go on, and on Sunday I will go on with the examples. So this is another very elegant visual explanation from a book that I really like from this course of Drongelen. It is in the course website. So if someone feels that he didn't fully understand it, everything is very, very good in this. So, sorry, 1 minute. So you can see here that what they did, they have this spike train over here, and then within each row, they shifted it. So you see all the possible shifts, right? So this is the spike number, and this is delta t in millisecond. And unfortunately, they didn't write here the number that they shifted. And then you can see that the autocorrelation over here, really nice to see it, I think. This is kind that you see that here it's high, and you see here that the distribution is high, and here it's 0 because of the refractory period. And then you have these horns that I don't know if Izal talked with you about them. Okay, so the horns are not due to the bursting activity. Okay, they are due to the fact that we have a reduced refractoriness in the signal. So we don't have really a higher level of neurons over here, although it looks like a bursting. And then it reduces until it stabilizes. And this is the firing rate of the neuron. Okay, so really 2 or 3 last things for your recitation quiz. So you have these toy problems of Poisson neuron. I will explain it again on Sunday. That for a fully Poisson without refractory, it looks like this. If there is refractory, you look here at 0, and then you have this rebounds over here, and then it stabilizes. And we have also these really nice autocorrelations of a burster that looks like this, okay? There is a higher probability for smaller time lags. And here, this is the oscillatory one. Okay, and you can see it only when you are calculating the autocorrelation. And the last thing is just only saying that you have the same idea with cross-correlation function. There is no chance that you understand now what I'm saying. I'm just running with no use. Okay. If you want to try and solve the recitation quiz today, you're welcome. And if you don't, you can wait to Sunday, and on Sunday I will complete from here, and I'll explain it more thoroughly, and I will give all the examples here and maybe add some more. And then you can try to solve the recitation quiz, okay? It's not really that hard, but maybe after we talk a bit more about this subject, it will be more clear. Okay? Yeah, I thought about it regarding the recitation quiz. Yes. I'm thinking about what to do. Maybe I'll talk about it also on Sunday. This is the right thing to do, okay? Because now nobody will listen. I look at you and I feel your sorrow. Your sorrow, I mean. Any more questions? Yes, Araceli. The maximal. So if you have a plot that you can squeeze, for example, if you have 200 milliseconds and from 100 there is no change, then I would put 120, 150. Good. Okay, did you see the clarifications regarding project 1? So I wrote you that the main thing is how you explain yourself. All the others are extras. And if you explain yourself good, even if you didn't fully write the exact algorithm for ergodicity break, but you write another one and explain yourself, and this is also measures the ergodicity, so there is no problem. Okay, so you will get full points. Okay, so this is also about ergodicity break and about anything in the project and in this course. This is a course for scientific thinking, and commonly each scientist finds a different way to apply these ideas that we're talking about. So this might be confusing, but it means that you have to be more creative and that you really have to explain yourself good, which is something that we don't do commonly in most of the courses. And this is a good place to start. Good. Enjoy. See you today evening if you wish. Only me. Why? The projects are my playground. The quizzes are her playground. Do you want me to turn off the microphone? Yeah, it's okay.